then I start. Thanks very much for this invitation. I'm going to talk about the standardization of a Attested TLS protocol that is being standardized in IETF SEAT working group, which is a new working group, which I will describe in my talk. And I have, or I want to first give a little bit of a background. So Hank and Michael already gave you a bit about the remote attestation side, and I will show you a little bit of the TLS side, and then how does the overall picture fit together in the whole ecosystem to something that one can actually use to transmit these attestations. And as I just asked, like protocol is very important. How do you actually transmit that kind of thing is really important. System model and goals. I will describe what do we actually mean by designing this kind of a protocol, under which assumptions we do that, and such kind of things. And I will briefly present some of the results and then summarize my talk with some backup in case of any questions. Here is the big picture. So starting from this side, as I said, so Hank and Michael talked about remote attestation and primitives. I mean that these are, let's say, attestation results, attestation evidence, and so on, all these conceptual messages which are here, and then composed together for different trusted execution environments. So in the context of confidential computing, which was mentioned in the very start of the workshop, ARM CCA, Intel SGX, Intel TDX, we have the formalisms for that. We formally represent these primitives into a language which is sound, and one can then argue about some properties on that, whether they are satisfied or not. And from the perspective of outreach, which I describe here in the dotted lines, which means that for the IETF RATS working group, we are contributing our primitives there. And CC Attestation SIG, I am leading a couple of projects there and contributing to another one. And Intel and ARM, because we have analyzed their technologies, so we have been giving feedback to them on their specifications. And what's not yet discussed is this top part, which is the TLS part. So remote attestation gives you some primitives. There has to be some wire protocol with which you actually communicate that over from, let's say, attester to the verifying relying party, which I mean the combination of verifier and the relying party. And that belongs to the TLS working group, which we have also contributed. And overall in the research groups, we have the usable formal methods research group, which is all these primitives we have been contributing there. As I said, so the combination of remote attestation and TLS is Attested TLS. And we have now a new working group, which is actually working on the standardization of the protocol, which is combining these two, which is this Attested TLS. And that's also part of the CC attestation SIG, a couple of projects as mentioned. And so protocol level is not all. We also need some system level architecture specifications, which means that we can do actual system analysis rather than just protocol analysis, which is then called as system level analysis. So that's the bigger picture of the whole thing, what we have been doing or what we are doing. And of course, collaborations are very welcome from the global platform or otherwise. And this is the block that I'm going to now zoom into and specifically talk about. So we formally view this as three different categories of attested TLS, meaning that I have two things which I showed on last slide, remote attestation and TLS. How can I combine them? And by combination specifically, the most important from cryptographic perspective is at what point in time I sign the claims, the attestation claims that Hank talked about. And if I do it in time perspective, going to the right, that's the start of the TLS handshake protocol. Client hello, the first message, client finish, the last message, and that's basically the span of the TLS handshake. If I do it before the start of the TLS protocol, that's pre-handshake attestation. If it's in between, that's intra-handshake attestation. And if it's after the end of the TLS handshake protocol, it's the post-handshake attestation. And then we have a bunch of different protocols, which are in each of these categories, meaning that for pre-intra post, there are several design options which are either existing or proposed. And specifically for global platform, the link I have put down here, so which is that it's intra and post handshake attestation protocols are there. However, I could not find real specifications of the protocol itself, so to say, in that document, which is to say that how exactly that evidence is put into that intra handshake protocol, what exactly happens there. And there is a description of the API, of course, but it's not clear how that is linked together with the TLS protocol and how that is transmitted. Of course, like transmission is there, but the binding is not very clear how exactly this is done. So what I'm going to do in this presentation is take the use case of confidential computing and a scenario which is that the TLS server, TLS has two parties, server or roles, server and client. So I will take TLS server as RATS attester. And the categories I'm going to talk about are pre and intra, while for post handshake, we have the analysis which is ongoing in the seed working group. So I have the system model and goals, which are going to be like this. That is, I have an infrastructure provider, which I am going to communicate with. I, meaning the client here, I as a TLS client and acting as a verifying relying party, combination of relying party and the verifier. I want to communicate with this on the cloud, for example. That can be one of the possibilities. I have a physical machine identified by IDS. And the verifying relying party by some means has got this attestation key public part in its trust store that, as Hank mentioned, could be the possibility that there is a complete trust chain, like you have the Intel's root key, public part of the Intel's root key obtained from some API from Intel, and then you build that trust chain up to the public key, which you get via this evidence, which I will show you. And a subset of that physical machine is the attester, which is the one which is being mired, CC platform, meaning the confidential computing platform. On top of that, there is a quoting agent, a generalized term, which represents the entity which is generating that evidence, signing the evidence with the help of this private attestation key. And on top of that, I am considering a virtual machine, namely a VM-based trusted execution environment. And within that VM, there will be this network stack, which will be communicating with this TLS client. So all the keys, I mean to show here that all the network keys, meaning the TLS handshake keys, are stored within this virtual machine and as part of the attester itself. And each VM has an evidence which collects all these claims I have represented via state one for this specific VM, and the public key corresponding to this, which is that I identify each of that VM. It could be multiple replicas, and there are replication attacks. So that's why it's important to identify specific VM versus other VMs from possibly from other tenants on the same machine. And then there was already a presentation about TPM. So this, the physical machine's key, physical machine which was identified by IDS is linked to this public part corresponding to this specific key, which is stored in either a HSM or a TPM in some form of, like it's protected separately from this attester. That's the main thing. With that, we have these informal security goals of what such a protocol design should actually try to achieve. And there are goals from remote attestation side, there are goals from TLS side, and then there is a composition of the two goals. And this is showing the remote attestation goals, which are that I have to ensure that the integrity of evidence is maintained, freshness of evidence is maintained. Hank talked about it already. From a formal perspective, we view it as binding evidence to a specific remote attestation interaction. That's one thing that freshness achieves. And the second thing that it provides you the recentness of evidence generation, that it was recently generated. The claims are still fresh. And then the third one is from a formal perspective that if this attestation key is known to the adversary, it should not be able to establish the connection. And similarly, the ephemeral key, which was identifying a specific virtual machine, if that key is known to the adversary, it should not be able to establish the connection. TLS has fairly standard goals and are well formally verified over several years, like from 2018 when TLS 1.3 was standardized, RFC 8446. And there the idea is that we have lumped together the keys property into this property, which is establishment of connection with client write key, which is the key with which the client writes or encrypts its secret finally after the end of the TLS protocol. And if this key is known to the adversary, it should not be able to establish this connection. And server authentication, that you identify that that the client has the same identity as the server actually has. So standard TLS, no changes in this. What we do propose in addition to remote attestation goals are also these composition goals. That is, the two are composed together correctly. And here there are interesting things. For example, evidence is generated by the same server that is authenticated, meaning that it should not have a relay attack. So to say that the one that I attest and the one that is being authenticated are the same. And that can be achieved formally via binding evidence to a specific TLS connection. And that still is not clear what that TLS connection is. So there are three keys within the TLS handshake key schedule. The first one, the shared Diffie-Hellman key, then the handshake traffic secret of the client, then the application traffic secret of the client. I will describe you in the next slides. And finally, the agreement of all remote attestation and TLS parameters, that all the parameters from remote attestation side and TLS, both client and server, have an agreement over those. With that background, I want to give you or show you basically the results of our analysis so far from the formal analysis in ProVerif. That's the state-of-the-art tool for formal analysis and formal proofs. As I said, for pre-handshake and intra-handshake, and for that we have taken a specific protocol which is interoperable RATLS, which was a proposed project and adopted project in the CCC attestation SIG, and this intra-handshake is or was actually a proposed draft in the TLS working group, and these are the results for these two protocols. In particular, the interoperable RATLS does not achieve the freshness because the evidence is pre-generated, intuitively clear. Otherwise, the server authentication property is not satisfied in either of those protocols, and also the binding and the agreement of all the parameters is not satisfied. I have here a link to the UFMRG talk that I gave a couple of weeks ago at IETF 124 for details to those whoever is interested. And then I have the results for proposed solutions. So what we did is we looked into how far actually we can go with the intra-handshake protocol, intra-handshake attestation protocol, and that's basically we came up with 5 solutions. And we then similarly analyzed for all these properties, all these 5 solutions to see what is the best guarantee or what is their level of security. And the first 4 solutions, which are modify certificate verify messages, add to certificate verify messages, or to define a new signature algorithm or have a new attestation message in order to transmit that evidence. They all achieve similar properties, which is to say that they have no binding to the TLS, to the TLS connection. And the 5th solution, which actually combines the solution 1 with defining a new exporter in order to bind the two, still achieves only up to binding up to the handshake traffic secret of the client. In the next slide, I will show you what that actually means. And that's basically this problem, which is that server and a client from TLS perspective, a tester and a verifying client party from remote attestation perspective, and assuming that the client actually has initially known reliable, authentic public attestation key of the server. The big diagram that I showed you at the bottom, there was this quoting agent with the private key of this attestation key. So that authentic key has somehow been already available to the client. And with that initial assumption, the problem here in the intra-handshake protocol is that if I want to have a strong binding, that is namely up to the finished message from the server side, if I need to have this binding, I have to, like this is one key which is dependent on this. And I have to, if I include this in the evidence has to be sent after of this message, namely after 2C, between 2C and 2D, and after generation of this, of course. And if I do that, this finished message, which is from the TLS perspective, which was containing a MAC over all of the previous messages, will actually then not contain the new message which is being transmitted here. And that basically means that the client will not have a guarantee that this specific message, which is this, is actually corresponding to the same server that I am communicating with. And it could still be then relayed over. And the problem with binding up to this point is that it's actually from a client perspective, the real thing is that it cares about the actual application traffic secret with which it's going to encrypt its final secret. So at the end of this handshake, this is the key with which, or a key derived from this basically, is the one with which the client will actually then send over its secret. And due to that specific reason, the evidence has to be linked somehow with this specific secret rather than this specific secret. And another reasoning for this specific linking to this one is that there are several reasonings, but to keep it short, I will say it actually transitively includes the previous things. So if you see this log fs, which is a running hash, means that it includes transitively all the previous ones. So a simple argument is that this key includes all that material previously, and also including this HTSC or the log of the server hello. So it transitively includes all the previous contributions and is thus stronger than the binding up to this specific secret only. And there are other reasonings which I will skip for now. And to summarize, I will say that there is from the formal analysis, the key analysis, the key insights we have got are that we need to bind that evidence to the infrastructure identity. Whoever is running that specific instance of the virtual machine, that's really important in order to prevent diversion attacks. Such that it's really coming from a specific, let's say, it's really metadata center that I'm communicating with, and not some server in someone's, let's say, basement. So it's